Hello and welcome to 10-3, Geometric Sequences and Series. A geometric sequence is sequence is geometric if the ratios of the consecutive terms are the same. So in the sequence a sub 1, sub 2, sub 3, sub 4, so on, it is geometric if there is a number r such that the second term divided by the first term is equal to the third term divided by the second term, and the fourth term divided by the third term, and so on and so forth. The number r is a common ratio of the sequence. So once again, it is a geometric sequence if and only if the ratio of each term, each consecutive term, is the same. So second and first term be the same as third and second, fourth and third, so on and so forth. So some examples of geometric sequence. The sequence whose nth term is 2n is geometric. For this sequence, the common ratio of the consecutive terms is 2. So for example, 2 to the second power, or 2 to the nth power, I'm sorry, the first term would be 2, the second term would be 4, the third term would be 8 because 2 to the third power is 8. 2 to the fourth power is 16. Well, if you take the ratio beginning at the first one, 4 divided by 2 is 2. 8 divided by 4 is 2. 16 divided by 2 is 2. Thus, you have a common ratio r of 2. The sequence whose nth term is 4 times 3n, 3 to the nth power, is geometric. For this sequence, the common ratio of the consecutive terms is 3. So if I take 4 times 3 to the first power, I get 12. 4 times 3 to the second power, I get 36. The ratio of 36 to 12 is 3. The ratio of 108 to 36 is also 3. So on and so forth. It just continues infinitely that you have this common ratio. The sequence of whose nth term is negative 1/3 to the nth power is geometric. The ratio of the consecutive terms is negative 1/3. You go from negative 1/3 to positive 1/9. Positive 1/9 to negative 1/27. Negative 1/27 to positive 1/81. The ratio of those terms is negative 1/3. If you were to divide 1/9 divided by negative 1/3, you're obviously left with a negative number. Negative 1/9 is divided by divided by 1/3 becomes 1/9 times 3/1, which then reduces to 1/3. So you have a consistent geometric sequence. The sum of a finite geometric sequence. The formula for the sum of the finite geometric sequence is as follows. Given that you have the sum of the geometric sequence that is finite, where you have a sub 1, then a sub 1 times r, a sub 1 times r squared, so on and so forth, the common ratio, the r is not equal to 1, you can then take the sum of it by saying that the sum of the sequence is equal to, of that sequence is equal to the first term times 1 minus the ratio to the nth power over 1 minus the ratio. What's key here, let me get my laser pointer, what's absolutely key here is notice right here, the sum of some sort of sequence that is geometric is equal to the first term times, you're going to have 1 minus the ratio, but you're going to raise it to the nth power. This nth power is going to correspond to this n that is on top of sigma. So the n on top of sigma is the upper bound of my summation series. This is my initial term. So whatever my initial term is, the initial term in my sequence, it's going to be multiplied by 1 minus the ratio to the nth power over 1 minus the ratio. So example 2, find the sum of the finite geometric sequence. In this case, I have 4 times 0.3 raised to the I minus 1 power. So the formula for the sum of the sequence is that the first term times 1 minus the ratio to the nth power over 1 minus the ratio. Now notice they have told us up here that we're looking for the sum through the 12th term. Our initial term is 1, and we're going through the 12th term. So as a result, I'm going to go in here, I'm going to say my first term is 4, because based on the equation, 4 is my initial term. My ratio is 0.3, so 1 minus 0.3 to the 12th power over 1 minus 0.3. Use a calculator to plug it in. That's really the easiest way to do it, and you get that the sum of the finite geometric sequence is 5.714. Now the sum of an infinite geometric series, with it going on forever and ever and ever, is simply the first term has this sum, the first term divided by 1 minus the ratio. So the differences here is all in this infinity symbol. This infinity symbol tells us we're going infinitely. There's no upper bound. The upper bound is quite literally to infinity and beyond. Feel free to pause that if you need to take notes. So, find the sum of the infinite geometric sequence. In this case, the infinite geometric sequence has an initial term of 4. It's going to the infinite upper bound, and it has a ratio of 0.6. So in this case, my sum, my sequence, would be 4 times 0.6 to the first power, then 4 times 0.6. And in this case, notice they told us to start with 0 plugging it in for n. So by doing so, 4 times 0.6 to the 0 power, then 4 times 0.6 to the first, to the second, to the third, so on and so forth. Well, the simple formula from the last page said take the initial term and divide it by 1 minus the common ratio. The common ratio was 0.6. 4 minus 1 minus 0.6, which gives you 10. So the sum of the infinite solution, or the sum of the infinite series, rather, is 10. In the next one, you have 3, 0.3, 0.03, 0.003. I don't have an equation for this one. They didn't give me some fancy schmancy equation. What they did give me was the term, and they gave me the subsequent terms. If I were to divide 0.3 by 3, I would get 0.1. If I were to divide 0.03 by 0.3, I would get 0.1. I have a geometric ratio progression. Every single one of them has the same ratio. The second term over the first term is 0.1. Third over second. Fourth over third. So now what I do is I can say my initial term is 3, and my term here is going to be negative, or it's going to be minus 0.1, my r. Okay, which gives me 3 divided by 1 minus 0.01, which will be the same thing as 10 over 3 in fraction form, or 0.33. Okay, you could just simply take this as is, plug it into a calculator based on this formula, press enter, and be done.